Imagine a construction site that never sleeps, because if the pouring stops for even 1 hour, the entire skyscraper could fail. We are diving into the high-stakes world of vertical slip forming, where hydraulic jacks must perfectly synchronize with concrete setting times to prevent catastrophic cold joints and structural discontinuities. It's not just construction, it's a relentless 24/7 race between chemical hydration and mechanical precision. Every second counts, every millimeter matters. Welcome to the world where megatowers rise without pause. Welcome back to Civil Engineering Edge, the channel where theory meets site reality. Today, we explore one of the most fascinating and high-speed construction technologies shaping modern skylines: vertical slip forming. From nuclear silos and bridge pylons to the world's tallest towers, this continuous concrete pouring system allows structures to rise day and night without stopping. If you are a civil engineer, site professional, developer, or student preparing for real-world challenges, this video will give you a deep technical understanding of slip form mechanics, structural behavior, equipment configuration, and site management principles. Let's elevate your engineering knowledge vertically. The engine of vertical growth. Vertical slip forming is not just a construction technique. It is a precisely engineered production system. At its core, slip forming transforms reinforced concrete construction into a continuous vertical manufacturing process. Instead of casting concrete floor by floor, the structure rises uninterrupted as formwork steadily climbs upward using hydraulic power. The principle is simple, but execution is complex. Freshly poured concrete must achieve sufficient initial set and green strength exactly at the same rate that the formwork moves upward. Typically, slipform systems climb at a rate of 150 to 300 millimeters per hour, depending on temperature, mix design, and structural thickness. This means that in 24 hours, a tower core could rise 3 to 6 meters, an extraordinary pace compared to traditional staged construction. The engine driving this vertical growth is a synchronized hydraulic jack system mounted on steel yokes anchored to embedded rods within the concrete wall. These jacks lift the entire formwork assembly, including working platforms, finishing decks, reinforcement crews, and equipment in a unified upward motion. Unlike conventional shuttering systems, slipforms never detach from the structure during operation. The concrete remains in a semi-plastic state as the forms slide upward, producing a seamless monolithic wall. This eliminates horizontal construction joints, significantly enhancing structural integrity and durability. Slip forming is commonly used for elevator cores in supertall buildings such as those seen in global icons like the Burj Khalifa, where core walls provide the primary lateral stability against wind loads. It is also used in chimneys, silos, bridge pylons, and shear wall cores. The real power of slip forming lies in its integration of materials science, mechanical engineering, structural design, and construction management into one continuous, high-precision system. It is the ultimate expression of vertical construction efficiency. Imagine a construction site that never sleeps, because if the pouring stops for even 1 hour, the entire skyscraper could fail. We are diving into the high-stakes world of vertical slip forming, where hydraulic jacks must perfectly synchronize with concrete setting times to prevent catastrophic cold joints and structural discontinuities. It's not just construction, it's a relentless 24/7 race between chemical hydration and mechanical precision. Every second counts, every millimeter matters. Welcome to the world where megatowers rise without pause. Welcome back to Civil Engineering Edge, the channel where theory meets site reality. Today, we explore one of the most fascinating and high-speed construction technologies shaping modern skylines: vertical slip forming. From nuclear silos and bridge pylons to the world's tallest towers, this continuous concrete pouring system allows structures to rise day and night without stopping. If you are a civil engineer, site professional, developer, or student preparing for real-world challenges, this video will give you a deep technical understanding of slipform mechanics, structural behavior, equipment configuration, and site management principles. Let's elevate your engineering knowledge vertically. The engine of vertical growth. Vertical slipforming is not just a construction technique. It is a precisely engineered production system. At its core, slipforming transforms reinforced concrete construction into a continuous vertical manufacturing process. Instead of casting concrete floor by floor, the structure rises uninterrupted as formwork steadily climbs upward using hydraulic power. The principle is simple, but execution is complex. Freshly poured concrete must achieve sufficient initial set and green strength exactly at the same rate that the formwork moves upward. Typically, slipform systems climb at a rate of 150 to 300 millimeters per hour, depending on temperature, mix design, and structural thickness. This means that in 24 hours, a tower core could rise 3 to 6 meters, an extraordinary pace compared to traditional staged construction. The engine driving this vertical growth is a synchronized hydraulic jack system mounted on steel yokes anchored to embedded rods within the concrete wall. These jacks lift the entire formwork assembly, including working platforms, finishing decks, reinforcement crews, and equipment in a unified upward motion. Unlike conventional shuttering systems, slipforms never detach from the structure during operation. The concrete remains in a semi-plastic state as the forms slide upward, producing a seamless monolithic wall. This eliminates horizontal construction joints, significantly enhancing structural integrity and durability. Slipforming is commonly used for elevator cores in supertall buildings such as those seen in global icons like the Burj Khalifa, where core walls provide the primary lateral stability against wind loads. It is also used in chimneys, silos, bridge pylons, and shear wall cores. The real power of slipforming lies in its integration of materials science, mechanical engineering, structural design, and construction management into one continuous, high-precision system. It is the ultimate expression of vertical construction efficiency, visualizing the relentless 24/7 motion of hydraulic jacks. Imagine standing on a slipform platform at midnight. The city is silent, but the structure is moving. Hydraulic jacks positioned along the perimeter of the formwork operate in synchronized increments. Each jack grips a vertical steel climbing rod embedded in the hardened concrete below. At controlled intervals, the jack extends upward by a few millimeters, then locks. When all jacks complete this micromovement simultaneously, the entire system lifts uniformly. This motion is continuous, not dramatic, not fast, but constant. Typically, lift cycles occur every few minutes. Over hours, this incremental motion accumulates into significant vertical progress. The synchronization is critical. If one jack lifts slightly faster than the others, the entire form could tilt, causing uneven wall thickness or structural distortion. Therefore, modern slipform systems use centralized hydraulic control units that monitor pressure, alignment, and elevation. Concrete behavior governs everything. The mix must achieve sufficient early age strength, approximately 0.2 to 0.3 megapascals by the time it exits the bottom edge of the form. If it sets too slowly, the concrete may slump or bulge. If it sets too quickly, it may bond to the form panels, causing tearing or surface defects. Temperature control becomes essential. In hot climates, retarders may be added. In cold climates, heating blankets or admixtures accelerate hydration. The construction team monitors slump, setting time, and strength gain continuously. This 24/7 operation requires shift-based manpower planning. Engineers, quality inspectors, surveyors, reinforcement crews, and finishers rotate in carefully coordinated cycles. Even minor delays in material supply, cement aggregates, admixtures, can disrupt the vertical progression. Slipforming is not simply about lifting forms. It is about orchestrating chemistry, hydraulics, geometry, and manpower in perfect harmony, continuously, until the tower reaches its final height. Anatomy of the slipform rig. A vertical slipform rig is a multi-level mechanical ecosystem designed for strength, stability, and productivity. 1. Yoke frames. The yokes are structural steel frames spaced along the wall perimeter. They connect the inner and outer form panels while supporting hydraulic jacks. These frames transfer lifting loads from the jacks to the entire formwork assembly. 2. Hydraulic jack system. Mounted on the yokes, hydraulic jacks grip vertical climbing rods cast into the concrete. Their synchronized action lifts the system uniformly. The rods remain embedded in the finished wall or are later removed, depending on design. 3. Form panels. Steel or plywood-faced panels define the wall geometry. These panels must resist lateral concrete pressure while allowing smooth upward sliding. 4. Working platforms. Slipform rigs typically include 3 levels. Top platform for reinforcement fixing and concrete placement. Middle platform for monitoring alignment and jack operation. Lower platform hanging scaffold for surface finishing, patching, and inspection. The hanging scaffold allows workers to correct minor surface defects immediately after the concrete emerges from the form. 5. Survey and alignment control. Laser plummets, total stations, and inclinometers continuously monitor verticality. A deviation of even a few millimeters per meter can accumulate into dangerous misalignment at height. 6. Material delivery systems. Concrete is delivered via pumps or cranes. Reinforcement is prefabricated in segments and installed ahead of the rising forms. The entire rig behaves like a climbing factory, self-contained, vertically mobile, and structurally integrated. Every component is engineered to handle dynamic loads, wind forces, and the constant upward motion. Traditional jump forming versus continuous slip forming. To understand why slip forming dominates supertal construction in 2026, we must compare it with traditional jump forming. Jump forming. In jump forming, formwork is assembled for a single lift height, typically 1 floor. Concrete is poured, allowed to cure, and then the formwork is dismantled and jumped upward using cranes. This method creates distinct horizontal construction joints at each lift. While suitable for moderate heights, jump forming introduces repetitive crane dependency, staged curing delays, potential cold joints, increased labor cycles, slower vertical progress, slip forming. Slip forming eliminates these stop-start cycles. Concrete is poured continuously, and the form climbs at a controlled rate without dismantling. Advantages include seamless monolithic walls, elimination of horizontal joints, faster core construction, reduced crane dependency, superior structural continuity for supertal structures where core walls resist immense wind loads. Monolithic integrity is critical. Consider skyscrapers like the Shanghai Tower, where structural efficiency and speed are paramount. Continuous systems dramatically reduce schedule risk. In 2026 mega developments, time equals money. Developers demand shorter project durations and slip-forming answers that demand by converting vertical construction into a non-stop process. However, slip-forming requires precise planning, experienced teams, and continuous resource availability. It is not forgiving. Once started, stopping is costly and technically challenging. In essence, jump forming is episodic construction. Slip forming is uninterrupted vertical production, the chemistry of continuous flow. Vertical slip forming is not only a mechanical operation, it is fundamentally governed by concrete chemistry. The success or failure of a slip form project depends on how precisely engineers control hydration kinetics, setting time, and early age strength development. When cement reacts with water, hydration begins immediately. The formation of calcium silicate hydrate CSH gel provides the binding strength necessary for structural integrity. In slip forming, the concrete must reach an initial green strength of approximately 0.2 to 0.3 MPa by the time it exits the bottom edge of the formwork. This strength is sufficient to maintain shape without lateral support. However, timing is everything. If hydration is too slow, the concrete may slump, bulge, or crack under its own weight. If hydration is too rapid, it can adhere to the form panels, causing tearing or surface defects during upward movement. To control this, engineers carefully design the mix width, optimized water-cement ratio, controlled slump typically 80 to 120 millimeters, retarders or accelerators depending on climate, high early strength cement grades, supplementary cementitious materials like fly ash or silica fume. Temperature plays a decisive role. In hot climates, hydration accelerates, increasing the risk of cold joints if pouring rates fluctuate. In colder environments, slower strength gain can delay vertical lifting. Therefore, real-time monitoring of ambient temperature, concrete temperature, and maturity index is essential. Continuous batching is another challenge. Unlike conventional pours, slip forming cannot tolerate interruptions. The batching plant must operate reliably for days or even weeks. Quality control teams conduct frequent slump tests, temperature checks, and Q-base sampling. The chemistry of slip forming is a balancing act between rheology, hydration rate, and structural demand. It transforms concrete from a passive material into a time-sensitive performance system. Precision under pressure. Slip forming is executed under immense structural, mechanical, and operational pressure. Precision is not optional, it is mandatory. As the slip form rig climbs, alignment must remain perfectly vertical. The deviation of just 5 millimeters per meter can accumulate into dangerous offsets at 200 meters height. Engineers rely on total stations, laser plummets, GPS positioning systems, and inclinometers to continuously monitor verticality. Hydraulic synchronization is another critical factor. Each jack must lift at the same rate and pressure. A mismatch can create torsional stress within the form assembly, resulting in uneven wall thickness or structural distortion. Modern systems use centralized hydraulic control units to maintain uniform lifting pressure. Wind loading introduces dynamic challenges. At greater heights, lateral wind pressure can cause sway in the slipform rig. Temporary bracing systems and wind monitoring sensors are deployed to maintain stability. Wind speed thresholds are predefined. Operations may slow if conditions exceed safe limits. Reinforcement placement must also keep pace with rising forms. Steel fixing crews work one level above the pouring zone, installing vertical bars and ties before the form reaches that height. Any delay in reinforcement delivery can disrupt the entire sequence. Survey engineers conduct frequent checks to confirm wall thickness, embedment accuracy, and opening alignment for doors and lift shafts. The system operates under continuous pressure, mechanical pressure from hydraulic systems, lateral pressure from fresh concrete, and scheduled pressure from developers. Yet, when executed properly, slip forming achieves millimeter-level precision across massive vertical heights. This level of accuracy under continuous motion represents one of the most demanding feats in modern construction engineering. The high-stakes execution. Slip forming is a high-risk, high-reward operation. Once the process begins, stopping is technically complex and financially costly. The primary risk is unplanned interruption. A breakdown in concrete supply, hydraulic malfunction, power outage, or severe weather event can disrupt the continuous cycle. If pouring stops for too long, cold joints may form, compromising structural continuity. Therefore, contingency planning is critical. Backup generators, redundant hydraulic pumps, secondary batching arrangements, standby maintenance teams. Manpower planning is equally important. The site operates in 24-hour shifts. Supervisors, engineers, surveyors, quality inspectors, and labor crews rotate in disciplined coordination. Safety risks increase with height. Workers operate on suspended platforms exposed to wind and weather. Strict safety protocols include guardrails and fall arrest systems, emergency evacuation ladders, real-time weather monitoring, continuous communication systems. Structural risk management is also paramount. Concrete pressure against form panels must remain within design limits. Excessive pour rates can cause blowouts, while slow rates can lead to bonding issues. Despite these risks, the reward is enormous. Accelerated schedules, superior structural integrity, and cost efficiency in high-rise core construction. Slipforming demands total commitment. It is not forgiving, but when executed with discipline and expertise, it transforms complex vertical construction into a controlled, continuous process. The future of monolithic skylines. As cities expand vertically, the demand for faster, stronger, and more sustainable construction methods increases. Slipforming is poised to become even more dominant in the era of megatowers and super talls. Future innovations include AI-based hydraulic synchronization, real-time concrete maturity sensors, BIM-integrated slipform planning, automated reinforcement installation, robotic finishing systems. Digital twin technology now allows engineers to simulate slipform progress before execution. Predictive models analyze hydration curves, weather data, and structural loads to optimize climbing rates. Megastructures such as the Jeddah Tower demonstrate the necessity of rapid core construction in extreme heights. Continuous systems significantly reduce core cycle time, accelerating the overall project schedule. Sustainability also benefits. Reduced crane dependency lowers fuel consumption. Monolithic walls enhance durability, reducing long-term maintenance. With advancements in ultra-high-performance concrete, UHPC, and smart admixtures, slipforming may soon achieve faster climb rates while maintaining superior surface finish. The future skyline will not be built in segments. It will rise in seamless vertical flows. Slipforming represents the shift from traditional construction toward industrialized vertical manufacturing. Structural design considerations in slipforming. Slipforming begins long before site execution. It starts at the structural design stage. Engineers must design reinforced concrete walls capable of resisting lateral wind loads, seismic forces, and construction stage stresses. Wall thickness must balance structural stiffness and constructability. Fresh concrete lateral pressure is calculated based on pour rate, temperature, and slump. Reinforcement congestion must be minimized to allow continuous placement without obstruction. Codes such as IS 456, IS 875 wind loads, and IS 1893 seismic design guide structural safety. Crack control, shrinkage allowances, and construction tolerances are carefully integrated to ensure long-term durability and monolithic performance. Concrete mix design strategy for slipforming. Concrete for slipforming is not ordinary site concrete. It is performance engineered. The mix must achieve early green strength within hours while maintaining pumpability and workability retention. Water-cement ratio is tightly controlled to balance strength and flow. Chemical admixtures such as retarders or accelerators are selected based on climate conditions. Temperature control is critical, especially in hot regions, where hydration can accelerate unpredictably. Continuous batching consistency is mandatory to avoid variation in setting time. The mix is tested for slump stability, early strength gain, and surface finish quality to ensure uninterrupted upward movement without bonding or surface tearing. Risk management and emergency shutdown procedures. Slipforming cannot afford uncontrolled stoppages. Therefore, risk management planning is essential. Backup generators ensure uninterrupted hydraulic operation during power failures. Redundant pumps and standby maintenance teams reduce mechanical downtime. In case of emergency shutdown, engineers plan controlled formation of construction joints with proper surface preparation for resumption. Wind speed thresholds are predefined to prevent structural instability. Concrete supply chain backups must be arranged to avoid cold joints. Emergency communication systems, evacuation ladders, and safety harness protocols protect workers operating at height. Proper contingency planning transforms slipforming from a high-risk process into a controlled engineering operation. Slipforming versus climbing formwork versus jump form. Slipforming differs fundamentally from climbing and jump form systems. Jump form construction proceeds floor by floor, requiring curing time and crane repositioning. Climbing formwork moves in stages, but still involves intermittent lifting cycles. Slipforming, however, operates continuously without dismantling forms, eliminating horizontal joints. It is ideal for silos, chimneys, and high-rise cores where monolithic integrity is critical. While slipforming offers unmatched speed and structural continuity, it demands constant resource availability and precision. Climbing forms offer flexibility, whereas slipforming offers maximum productivity. The choice depends on project height, structural design, risk tolerance, and schedule constraints, cost analysis, and project economics. From a developer's perspective, slipforming is an investment in time efficiency. Although initial equipment mobilization and specialized labor costs are higher, the overall project duration reduces significantly. Faster core construction enables earlier floor cycles, accelerating return on investment. Reduced crane dependency lowers fuel and operational costs. Continuous operation optimizes manpower shifts and minimizes idle time. However, slipforming may not be economical for low-rise or irregular structures. Its economic advantage becomes evident in tall, repetitive vertical elements. When schedule compression and structural integrity are priorities, slipforming often delivers superior life cycle value, common site failures, and lessons learned. Slipforming requires vigilance to prevent failures. Excessive pour rates can cause formwork blowouts due to high lateral pressure. Uneven hydraulic lifting may lead to wall misalignment. Inconsistent concrete setting can cause surface tearing or bulging. Reinforcement delays can halt vertical progression. Cold joints may form if pouring is interrupted beyond allowable limits. Wind-induced sway at high elevations demands continuous monitoring. Lessons learned from major projects emphasize disciplined supervision, real-time quality checks, and coordinated material supply. Most failures arise not from design flaws, but from operational lapses. Strict site control ensures successful monolithic construction. Digital and smart construction integration. Modern slipforming integrates digital technology for precision and efficiency. Building Information Modeling BIM enables pre-construction simulation of climbing sequences. IoT-based maturity sensors monitor real-time concrete strength development. AI-controlled hydraulic systems automatically synchronize jack movements to maintain vertical alignment. Laser scanning and drone inspections verify geometric accuracy at height. Cloud-based dashboards allow engineers to track progress, temperature, and structural deviations remotely. Digital twin models predict potential alignment errors before they occur. These smart integrations reduce risk, improve quality, and enhance productivity. The future of slipforming lies in merging continuous concrete flow with intelligent construction systems. A true and best example. One of the most iconic examples of slipform technology is the central core construction of the Burj Khalifa in Dubai. Standing over 828 meters tall, This engineering marvel required an exceptionally strong and rapidly constructed reinforced concrete core to resist extreme wind loads. Slipforming was used to construct the reinforced concrete walls efficiently and continuously, ensuring structural monolithicity and alignment accuracy. The project team implemented strict temperature control measures to manage hydration in Dubai's intense heat. Ice was added to the concrete mix, and pours were scheduled strategically to prevent excessive thermal stress. Hydraulic systems were carefully synchronized, and vertical alignment was continuously monitored using advanced surveying equipment. The result was a structurally continuous, high-strength core that formed the backbone of the world's tallest building. This project proved that slipforming is not merely a technique. It is a critical enabler of extreme vertical construction. This is the power of engineering without pause, where chemistry, hydraulics, and structural science unite to raise giants from the ground. Vertical slipforming is not just construction technology. It is a symbol of precision, endurance, and innovation. If you are serious about mastering real-world construction systems, subscribe to Civil Engineering Edge and elevate your knowledge beyond textbooks. Share this video with fellow engineers, students, and site professionals who want to understand how modern mega towers truly rise. Until next time, keep building smarter, keep building higher, and keep pushing engineering to the edge.